All right, guys, chapter 2. Okay, what we're basically going to do is go through my PowerPoints. I'm going to read them off to you, point out and explain stuff. Feel free to watch them a couple times, take notes. If you have any questions, make sure you ask. When I give you questions to do, they should be done. Show your work, take a picture, load it up, and make sure you hit submit. Okay? All right, so we got here. All quantities in physics can be categorized as either a scalar or a vector quantity. A scalar quantity has magnitude, which means amount only, all right? No direction, okay? Like 4 meters, 3 seconds, $5, those are all scalar quantities, okay? A vector quantity has magnitude with direction, like 4 meters north or 5 newtons east, and a newton is a unit of force, okay? So if it has a direction, then even if it's up, down, left, right, it's a vector, okay? A vector is drawn as an arrow to indicate direction and a length proportional to the quantity. So if I said we're going to go 6 meters east, I would have this arrow be 6 centimeters long, and I would have a scale of 1 meter equals 1 centimeter, okay? So if you draw the arrows correctly, then what you'll end up doing is you'll have a graphical representation to scale. All right, longer arrow, longer distance, okay? Distance is the length the object travels. Displacement is the length with direction from the beginning of the journey to the end of a straight line. So here's an example. A student walks 5 meters east and then 12 meters north. The total distance he walked was 17 meters, but the displacement would be, using Pythagorean theorem, 13 meters at 67 degrees north of east. And you'd use geometry for that. The distance a body moves per unit of time is called speed. There is instantaneous speed, average speed, and final speed. Instantaneous speed is the speed you are going at that moment. You're in your car driving down the road. You look down, it says 60 miles an hour. That is your instantaneous speed. Okay? Average speed would be the total distance traveled divided by the total time in the car. Okay? That would be your average speed. Now, the final speed, for that, you would have to assume that we have what we call an acceleration. Okay? So let's say you start from rest and you're increasing your speed 2 meters per second, every second. You know, how fast are you going at the end? That would be your final speed, okay? And in physics and Regents physics, we deal with constant accelerations, all right? We don't deal with fluctuating accelerations. Like, let's say you drop an object, all right, from the sky. It's going to start falling with an acceleration of 9.81 meters per second squared. All right, it's going to get faster and faster and faster and faster. But then air resistance pushing back up, it's going to cause it to accelerate slower and slower and slower until it hits a thing that we call terminal velocity, where you can't go any faster. Like if you jump out of an airplane, most people's terminal velocity is somewhere around 80 miles an hour. You can't go faster. How can you slow down? Change your surface area, right? More surface area, the slower you would go. Jumping into a pool and you go like a pin dive, all right, you go faster, all right? Those things can be affected. In Regents physics, we deal with, we basically neglect air friction. And so all the accelerations are constant, okay? So if we look at this one, it says, how fast is a car moving if it goes 30 meters in 5 seconds? Now, 30 meters is a measure of distance, all right? D is distance. This is the delta symbol. Delta means change. Okay, the change is from 0 to 30 is 30 meters, and the change from 0 seconds to 5 seconds is 5 seconds. So 30 over 5 would give us 6 meters per second. So the units for speed and velocity are meters per second. Okay. Average velocity is the sum of the initial velocity and the final velocity divided by 2. Okay, so if we had an object, we're dropping it, it starts at 0 and goes to 10, all right, the average velocity would be 5, okay? So there's 2 different average velocities. The one where it's the trip, and the other where there's an acceleration, okay, or a deceleration. So final plus initial over 2. I'll be honest with you. Your first test question, I usually do something like a car is moving at 2 meters per second and accelerates to 10 meters per second, and I give you like 4 seconds. And I ask you, what's the average velocity? That the time was just unnecessary information, okay? You just use the 2 velocities I give you, add them together, divide by 2. That's your average velocity. Okay, you're going to see that on tests. Every year I give it to you, and half the people miss it because they start dividing by the time, which you don't do. Okay, and then this would be the average velocity for a trip, distance over time. And don't forget, you guys have a reference table, and we are going to be in the mechanics section of the reference table. All right, now we're going to talk about distance versus time graphs. Okay. And I'm going to go through a couple different scenarios here so that you get an idea of what's going on. If you look at a graph, you should be able to tell what's happening. And if you can really do something, if you really know what you're doing, you can even tell a story about it. Okay. So for the first one, distance is on the Y and time is on the X. In fact, time is going to be on the X axis probably every graph this year when time is part of the thing, because time is an independent variable. All right. So, straight line going diagonally downward. All right. What that means, it's constant speed, negative direction. And negative direction means something's coming towards you. If I was to throw a ball to you, okay, to me, the distance would be increasing away from me. So it would actually go like that. It would go upward. All right. To you, the ball's coming towards you. All right, so it's getting closer and closer and closer. And if you think about this axis, what is on this axis? 0. 0 meters is where you're standing. So the ball's coming to you. So if you're playing catch, this is someone throwing a ball to you. It's moving at constant speed. There's no curve. Okay. All right, so that's that. Next one, same distance as time goes on. Standing still. You're not moving. Okay. This one is decreasing velocity, okay? Now, if you look at this graph, okay, it starts out and it's moving a large distance in a very small amount of time. Then it's moving a smaller amount of distance in that amount of time. And then it's barely moving. It's almost horizontal, okay? So in this case, you're decreasing velocity. It's coming towards you, all right? So we say that it would be decelerating, or a negative acceleration, okay? This one is the exact same thing, but this one is moving away from you, okay? So it's moving and then it's slowing down, slowing down, slowing down, and it probably stops right about here, okay? So it's decreasing velocity. This would be a decelerated curve, okay? Now, when you have a distance and a time graph, all right, the slope of all these graphs gives you velocity, okay? So if it's a horizontal line, what's the slope of a horizontal line? 0, all right? It's not moving, staying still, okay? This one here, if you did a rise over run, you would get a negative speed because it's going downward, right? It's coming towards you, but the slope of this line would be how fast it's moving, okay? This one here, this would show a positive acceleration. All right, this would be like you're throwing a ball off a bridge, and it's getting faster and faster and faster and faster because it's covering a larger and larger distance. Okay. Any curved one, see how curve, curve, and curve shows an acceleration or a deceleration. All right. On a distance versus time graph, you're always going to have either diagonals this way, or if I had a diagonal like that was this way, it would be constant speed, positive direction. Okay. So maybe you want to add that maybe to your graphs. You know, do one that goes in that direction. Okay. All right. So that's chapter 2.